Okay, so today we're going to be talking about the area between two curves, which is in Chapter 7, Section 1 of your textbook. Okay, so the definition for an area of a region between two curves states that if f and g are continuous on the interval from a to b, and g of x is less than or greater than f of x, or less than or equal to f of x for all x, then the area of the region bounded by f and g in the vertical lines x equals a and x equals b is a, this is the area, equals the integral from a to b of f of x minus g of x dx. So basically what we're saying is when you have two functions, f and g, so this is your graph, you have two functions, one going like this and one going like that, and you're trying to find the region between these 2 points. You're going to take f of x, this is f of x, and g of x. You're going to subtract g of x from f of x on the integral from a to b, and that's going to be your area. So moving on from that equation, we're going to do one problem. So it's asking us to find the area of the region bounded by x squared plus 2, y equals negative x equals 0, and x equals 1 on the interval from 0 to 1. So I already graphed it with a quick and simple sketch. You'll see, we have y equals negative x, we have x squared plus 2, and they're between x equals 0 and x equals 1. So this right here, this whole section is the whole area that we're looking for. And right here, this is our representative rectangle, and that helps to help us define whether this is like a dy, dx problem and how we're going to go about solving it. So from here, we have the change in a, that's the area, which is f of x minus g of x delta x, that's the general. So when we plug in our equation, we're going to get x squared plus 2 minus negative x, change in x. So from there, that's where we plug it into the integral. So we have a equals the integral from 0 to 1, because we're going from 0 to 1, of x squared plus 2 minus negative x dx. Okay, so just solving this out. And then when we take the antiderivative, we're going to get over 2 plus 2x evaluated from 0 to 1. Plug in all of this, we should get 1/3 plus 1/2 plus 2. And this is going to give us 17/6. Now you see that's so much easier than trying to find multiple representative rectangles throughout. By simply taking the integral and subtracting the bottom from the top, we can get the area. Okay, now there is another type of area between curves that we can find. We can find them for graphs that intersect. So this is going to be when the two graphs intersect instead of just being defined by two vertical lines. So when we get the graph of 2 minus x squared and g of x equals x, this is kind of our rough sketch, and we see that they intersect. And now let's say for the sake of the problem we don't know where they intersect. How do we find this out? Well, we set them equal to each other. So we're going to have x squared equals x. We're going to carry everything over. We're going to factor. And we're going to get x equals negative 2 and x equals 1. And obviously on the sketch we can see that that's where the points are, but if you were given uglier equations or an uglier graph, you would set them equal to each other to find them. So this is going to be our integral from negative 2 to 1. So from there, we plug it into our general formula. So remember, with change in a equals f of x minus g of x delta x, which is 2 minus x squared minus x. That's this part of the function. So I'm going to plug it into the integral. We're going to go from -2 to 1 of 2 minus x squared minus x dx. We're going to take the derivative, so we're going to get negative x cubed over 3 minus x squared over 2 plus 2x, evaluate it -2 to 1. Plug all of this in, and after doing that algebra, you should get 9/2. So a little bit more work than when they give you the region that it's bounded by, but all you have to do is set the two graphs equal to each other, and you should be able to get your answer from that. Okay. Now, there can be a time when your graph has more than 2 intersection points. When you're given a graph such as 3x cubed minus x squared minus 10x, and the graph of g of x, which is negative x squared plus 2 of x. Now we see when we sketch these, they intersect at more than 2 points. So we're going to do the same thing, though, to try and find those intersection points. So x squared minus 10x equals negative x squared plus 2x. So we set them equal to each other. Begin doing all that algebra. And from this we see that x, the intersection points are at x equals -2, 0, and 2. And that's about right on our graph. So when we have 3 intersection points, we can't just have one integral. We can't go from -2 straight to 2. We have to go from -2 to 0, and then from 0 to 2. Otherwise, we're going to get a wrong answer. So first, we're going to have to start out from a equals -2 to 0 of f of x minus g of x. And that is going to be 3x cubed minus x squared minus 10x plus x squared minus 2 of x. It's kind of ugly. We're going to simplify all of this, and after we take the derivative, we're going to skip a few steps. We're going to get to 3x to the 4th over 4 minus 6x squared, evaluated at -2 and 0. So for when we plug that in, this is going to give us 12 minus 24, and that's the first part. So, and then we're going to take the integral from -2 to, or 0 to 2, my bad, 0 to 2. And this is going to be g of x minus f of x, because we see from 0 to 2, g of x is actually higher than f of x. So it's top minus bottom, so we're going to take g of x here. So this is going to be negative x squared plus 2x minus 3x cubed plus x squared plus 10x. Simplify that down, take the antiderivative, and we're going to get negative 3x to the 4th over 4 plus 6x squared, evaluated at 0 to 2, and this should give us negative 12 plus 24. So we add these two terms up together. This is 24 minus 12 negative. So this is going to give us 24. And that is the area of our region. Now, if we had taken the integral from -2 to 2, that would have been wrong, and that would have given us an answer of 0. So when you have more than just 2 intersection points, you have to split up the integrals. Now, for our last problem, we're looking at a horizontal representative rectangle. And what this means is that we are taking the antiderivative with respect to y. And this ends up being much easier, because if we were taking it with respect to x, we would have, our graph would look somewhat rough sketch. we'd have to take it twice. We'd have to take one over here and one over here, and it's a lot more difficult to do that. If we take it with respect to y, we only have to take the integral once. Now, since there is no top and bottom function, you subtract the left function from the right function. So we see that the right function is 3 minus x equals 3 minus y squared, and the left function is x equals y plus 1. So when you do all of this math, and we see our intersection points are at -2 and 1, we get our answer of 9/2. If we had done it with a vertical representative rectangle and had to take the derivative, the antiderivative with respect to x, we would have had to do a bunch more work. So you can do it either way, but usually if it's in terms of y, it's a lot easier to take it this way.